喂喂，王老师。
哎，你好，你好。
哎，我是杨杰，对对，我改了一下名字。
哎，哦，哈
对，刚才好像可以看到，好像挺正常，声音也可以
啊，
听到，对，声音可以。
行行行。我把视频打开看看。对。
嗯，可以的，可以的，可以的，王老师。
行行行。好的好的。
对，待会儿我可能到那个，对，反正就应该王老师7点准时开始就行，我可能会提前半分
啊，
钟，然后就开始推流了，对。
好的好的好的。
嗯，好的，好的，行。
行，好，辛苦辛苦。
啊，没有没有，王老师要辛苦。
Hi, Professor Song Chu and Professor Zhe Yuan. Now we start. Good evening, everyone. Can you hear me?
Yes, we can hear you.
Okay, yeah. Okay, yeah. Good evening, everyone. Welcome to the 32nd edition of the AsiaGraphics webinar. I'm Weiming Wang from Nanjing University of Science and Technology. And I'm honored to serve as the host for today's session. As always, our webinar aims to spotlight the latest and most exciting advances in computer graphics and related fields, connecting researchers and practitioners from across Asia and beyond. Today, we are privileged to have two distinguished speakers presenting on topics at the cutting edge of visual computing and human AI collaboration. Our first talk is titled Constructing Radiance Field in Low Light Environment, given by Professor Song-Yong Chu. Professor Song-Yong Chu is an associate professor at Postech. Before joining Postech, he was an assistant professor at Digis from April 2017 to August 2019. He also worked for Samsung Electronics as a senior engineer from April 2014 to April 2017, and for Adobe Research as a research scientist in Seattle from March 2012 to March 2014. He received his PhD degree in computer science from Postech in February 2012 and bachelor degrees in computer science and in mathematics from Postech in 2005. His research interests include computational photography, image video processing, image restoration, etc. Now let's welcome Professor Song-Yong Chu. Please.
Okay, thank you for the introduction. Can you hear me? Hello,
Yes,
can you hear me?
Yes.
Okay, great. So, okay, let me start. So, good evening, everyone. My name is Song-Yong Cho, and thank you for coming to the talk. And the title of my talk today is Constructing Radiance Fields in Low Light Environments. So, sorry. Okay, then. Yeah. So radius fields have become a powerful tool for 3D scene reconstruction, and techniques like neural radiance fields, planar cells, and 3D Gaussian splitting, and so on have shown really impressive results recently, and a tremendous number of papers have been presented for the past few years. But these approaches actually, these radiance field construction approaches assume high quality input images, but in reality, various degradations can happen. For example, especially in low light situations, images often suffer from noise due to high ISO setting and also blur due to low exposure. And these degraded images may significantly degrade the quality of radiance field reconstruction too. So in this talk, I'm going to introduce some of the recent research to handle such degraded images in radiance field reconstruction. And I'm first going to introduce some recent research for radiance field construction from noise images. And then I will introduce approaches that consider blur and noise too. And in this talk, I'll focus more on the second part, which includes our recent research, Deep Blur RF, which was presented at CVPR this year. Okay. So, okay, let's first delve into the approaches to handling noise images for radius field reconstruction. So to handle noise images captured in low light conditions, Miller et al. Presented RONORF at CVPR 2020 2022. And as the title of this paper suggests, RoNeRF aims at NeRF reconstruction from high dynamic range for high dynamic range novel view synthesis from noise raw images captured in low light conditions. So to better understand the proposed method, we first can see, actually this figure illustrates the key idea of RoNeRF. So here, when you capture an image, we first capture the image in the raw space, camera raw space, and this raw data is processed by the camera ISP. I'm sorry, ISP, and we have an sRGB image. And basically, when you construct the radiance field, we actually capture multiple images, so we have multiple sRGB images in this stage. And then using these sRGB images, which are actually low dynamic range images, we use them to train NeRF, and then we render novel views. And these novel view images are low dynamic range images. So this is the conventional NeRF pipeline. And the proposed pipeline in this paper is shown on the bottom here. Let me just clear this. So instead of using sRGB images when reconstructing NeRF, the proposed system uses raw data as is. So the proposed system uses these raw images and directly train RoNeRF using raw images, and then using this trained NeRF, we can render HDR images in the raw space, camera raw space. And here, why this is called HDR views is because raw images usually have like a more larger dynamic ranges than sRGB images, because raw data are usually represented in 10 or 12 bits or sometimes 16 bits. And on the other hand, sRGB images in JPEG, they are represented using 8 bits. So basically, raw data uses more bits, and so because of that, raw images have larger dynamic ranges. And then after rendering HDR views in raw space, we can apply camera ISP as a post-processing step, and then we can obtain this sRGB image. And actually, so when you in the conventional NeRF pipeline, here in this ISP step, we apply, for example, image denoising to each image. So as this image denoising uses the information only from a single image, the performance of this denoising is pretty limited. So because of that, even if the ISP applies the image denoising, the post-processed sRGB images may have remaining noise and may lose some high frequency details. So because of that, even if we train NeRF and we render novel views, these novel images have low qualities. So instead of this, in this RoNeRF pipeline, we just directly use the raw data, and in this raw data, as we average the complementary information from multiple views, we can naturally suppress noise in the raw data. and also as we use multiple images here, when you're averaging, when you train RUNERF, we can more effectively suppress noise compared to single image denoising. So so here it's like we are applying multi-frame image denoising. So we can more effectively remove noise, and then we can render novel views. So as a result, we can render a higher quality images in this as a result of this process. So let me show you some examples here. So these are on the left, we have noisy input images, and these results are actually single image denoise. These images are the results of single image denoising and conventional NERF pipeline. So as you can see here, the novel view images are rendered from this pipeline still have remaining noise, and some of the high frequency details are lost. And these results these results are produced by applying video denoising and NERF. And as video denoising uses multiple input noisy images, it can actually achieve higher quality image denoising results, but still this process cannot sufficiently suppress image noise, so the rendering results still have some remaining noise. In contrast, this one is the result of the proposed system, and as you can see here, the rendering results have really high quality details and minimal noise. And more than that, actually this one is designed to produce HDR images. So first, let me show you the denoising results here. So as you can see here, using this RUNERF process, we can render really clean novel views. And also, we can this RUNERF also supports high high dynamic range images, so that we can actually adjust the exposure of the image later. So as you can see here, we can dynamically change the exposure of the rendering result like this. And there are a couple of other works that share similar ideas to RUNERF. Another one is NAN, which was presented at CVPR 2022. And this is actually for image denoising instead of NERF. So basically, when you capture an image in a real low light conditions, due to the small amount of light, we have to use really extremely high ISO values. So because of that, noises are severely amplified, and then we get this kind of really noisy images. So on the right, we have the result of NAN, noise aware NERF for burst denoising. So this proposed method is designed for burst imaging. So burst imaging here means a technique that captures multiple images. And the main challenge in burst imaging is, so the goal of the burst imaging is to capture, capture multiple images and to aggregate information from those multiple noisy images to obtain a single high quality denoising result. Okay. So and the main challenge in the burst imaging is how to robustly align the input noisy burst images. And to tackle this challenge, NAN uses IBR-LAN, which is presented as CVPR 2021, to find correspondences across different views. And IBR-LAN is actually a feed-forward network for feed-forward your radius field reconstruction. Okay, so we have the proposed pipeline is like this. So here we have n input images, and these input images are captured in low light conditions, so they may have a significant amount of noise. And then we extract features from these input images, and then using the features, we perform IBR-LAN to find correspondences between the input images. So IBR and then using the found correspondences, it aggregates information from different views and averages them to compute the denoising result. And and there is another work that is pretty similar to HDR nerf, row nerf, and this one is called HDR nerf, which was presented at CVPR 22. And this one is designed for also high dynamic range neural radiance fields. And so it also takes multiple low dynamic range images as input, and it reconstructs radiance fields of large dynamic range, and so that we can render novel views of high dynamic range. Okay, but this one is not designed for like denoising or for handling low light conditions. And let me just skip this part. And similar ideas have been also used for Gaussian splatting too. So nowadays, Gaussian splatting, 3D Gaussian splatting is more popular than NeRF. So similar ideas have been also adapted for Gaussian splatting. And one example is HDR Gaussian splatting here. So the basic idea is pretty similar, but they used the similar idea to the Gaussian splatting. Let me just skip this part. And let's move on to the second part, radiance field from blur images. So the task of radiance field reconstruction from blurry images is like this. So we have blurry training views like this, and we reconstruct the radiance field using these blurry training views, and somehow we remove blur and we reconstruct a sharp radiance field, and then so that we can render sharp novel views from this radiance field. Okay, so this is the goal of the radiance field reconstruction from blurry images. So to solve this problem, deep blue nerf was first proposed at CVPR 2022. And this diagram is from the paper of deep blue nerf. And this figure actually describes the overall pipeline of deep blue nerf, but personally, I don't think this diagram is really effective in conveying the key idea of deep blue nerf, so I prepared some other figures. Okay, so let me explain the key idea of deep blue nerf this way. So actually, this figure describes how image is captured in the 3D real world. Okay, so we have a 3D target scene, and we have 3D object here, and we have a camera. And when you take an image of this 3D object, the captured image is captured like this. So there is a center of projection or center of camera, and we can project a ray. We can cast a ray like this, and this from the center of projection, and then there is an intersection. So this is basically image plane. and we can find the intersection here between the array and the image plane, and the pixel value at this intersection is determined by the pixel value from the 3D object. So this describes the basic image acquisition process. Okay, so NeRF models radiance field based on this 3D model, image acquisition model. So here on the right we have another figure that describes how the NeRF models radiance field. So here we have a virtual camera, and we have 3D information, and this 3D information is stored in this MLP. And this 3D information corresponds to the radiance field. And at this using this virtual camera, we can render an image like this by sampling by casting rays like this from the center of projection. And along this ray, we sample multiple colors, and then we aggregate them to determine the pixel value at a particular pixel on this rendered image. And so NeRF trains this MLP by rendering this image and by comparing the rendered image against the input image. And so basically we compute the difference between the rendered image and the input image, and then we backpropagate the gradient back to the MLP, and we update the parameters of the MLP from using multiple input images. And once the MLP is trained, we can render novel views from for other viewpoints. So this is basically how the NeRF models radiance fields. Then what about when we have blurry images? So this figure describes how a blurred image is captured in the real world. So basically, when there is a camera motion or camera shakes, the center of projection of the camera moves like this during the exposure time. So because of that, for each pixel position, we have multiple rays coming from different positions of like this. So we have multiple rays, and we have the colors from these multiple rays are averaged together, and a single pixel value is determined on this blurry image. So because all these pixel values at different locations are aggregated together, we have this blurry image. Okay, and deep blue NeRF models camera shape based on this model. So again, we have an MLP here, and this MLP models sharp radiance field or sharp 3D information. And we have another MLP, and this MLP models per pixel ray jittering, or it describes camera motion during the exposure time. Okay. So for each pixel, we to render a blurred image in this model, we basically sample multiple rays per pixel. For example, we may sample like 5 rays per pixel, and this MLP provides different offsets, the offset of each ray at each pixel. And by averaging pixel values from multiple rays, we can render blurred images like this. And then we can compare the rendered image and the input image, and we can compute the difference, and you can backpropagate the difference to train both both of this MLP and this MLP. Okay, so these two MLPs are trained in an end-to-end fashion. And once these two MLPs are trained, then we can simply use this MLP to render sharp novel views. Okay. And after deep learning, a number of different variants of deep learning have been proposed. For example, so in the original framework of deep learning, we have two different MLPs. And for this one, we may use, for example, different 3D representation instead of MLPs. So we may use a voxel grid or 3D Gaussian splitting. So according to different representations, there have been presented different papers like this. And also, a number of different papers have been also presented to propose different models or different constraints or different priors for this camera motion modeling. So the key idea, even though there have been a number of different papers have been published for the past a few years, the key idea here is basically very similar. Okay. And actually, so these approaches share very similar limitations because they share the similar key idea. And actually, this deep learner, the key idea of deep learner is actually very similar to the traditional blur model-based deep learning approach. So here on the right, this figure describes the traditional blur model-based traditional blur model for image deep learning. So we have a blurred image, and this blurred image, this blurred image is modeled as a combination of as the convolution operation between the blur corner and the latent sharp image. And this blur corner describes the camera shake. Okay. And so this blur corner, actually this blur corner corresponds to this MLP, and this latent sharp image corresponds to this MLP that describes this sharp radiant field, and this convolution operation corresponds to multiple ray sampling in this deep learner framework. Okay, and in fact, there are actually many traditional multi-frame deep learning approaches based on this traditional convolution-based convolution-based blur model. Okay, and these approaches take multiple blurred images of the same scene like this, and then they simultaneously estimate the blur corner for each input blurred image and the latent sharp image by aggregating information from these multiple input blurred images. Okay. And but the problem is that the traditional blur model-based multi-frame image deep learning approaches have many limitations, many technical limitations, and also similarly, deep learners and each variant share really similar limitations to with these traditional blur model-based deep learning approaches. First, the deep learner and each variant they rely on linear blur models, which means they perform simple averaging of multiple rays per pixel. So because of that, they cannot handle nonlinear outliers and severe noise that cannot be described by linear blur models. For example, in this example, we have a training view here, and this light streak is not modeled by this light streak cannot be modeled by simple ray averaging. So because of that, when you have these light streaks, deep learner and BACs, they cannot reconstruct the sharp radiance field. And so if we render novel views, then the novel view images may have remaining artifacts like this. And also, when you have severe noise in input images, such severe noises cannot be modeled effectively by linear blur models. So previous deep nerve approaches, deep nerve-based approaches cannot reconstruct sharp radiance fields, and if we render novel views, and the novel images may have remaining noise like these. Okay, and here Bax is basically this one is based on Gaussian splitting, but basically the key idea is very similar to deep nerve. And the second limitation is that these deep nerve and each variant, they do not really use any priors on sharp images, but they rely solely on complementary information from different views to reconstruct sharp radiance fields. So because of that, they may fail when all input views exhibit similar blur directions. For example, here we have multiple input blurred images, and these input blurred images actually have the same blur, similar blur. Okay, and because of that, if we apply deep nerve for Bax, then these methods fail to reconstruct sharp radiance fields. Because they register no complementary information between in these images. So if we render novel views, then the rendered novel images still have remaining blur like this. Okay. And the third limitation is that they are really slow in the training time. So in the training time, they need to sample multiple rays per pixel. Okay, so if, for example, if for example here n is 4, then it means that to render a single rendered image, single blurred image, we need to sample 4 rays for each pixel, and it means that the rendering time takes the rendering time is 4 times slower than the rendering time of the conventional nerve. So it means, and as a result, the total training time is 4 times slower than 4 times longer than the training time of the conventional nerve. And usually we need more than 4, basically, especially when you have large blur. So it becomes significantly slower when as the number of rays increases. On the other hand, in image deep learning, recent image deep learning approaches, they no longer use the traditional convolution-based blur models. Instead, they adopt feed-forward deep neural networks that directly predict deep blurred images from input blurred images. So thanks to that, and this kind of deep neural network-based image deep learning approaches have been extensively studied for several years now, and they have been shown very effective in handling severe noise and nonlinear outliers as well. And also, as they use feed-forward networks, they are really computationally efficient. So, then the most naive idea to reconstruct the radiance field from blurred images would be a naive combination of DNN-based image deep learning and radiance field reconstruction. Specifically, we may construct a pipeline like this. So we have a blurry training views, and we perform single image deep learning to each training image, and we obtain deep blurred training views like this. And then we use these deep blurred results to reconstruct the radiance field, and then we can render sharp novel views. But this naive approach does not really work well, which is in fact already shown by the authors of deep nerve in their paper. And so here we have an example. So this is the result of the naive combination. So as you can see here, the rendered novel images, this rendered novel image still have some distortions and some degradations, and the details are not really accurately restored, and it still has some remaining blur. And this is due to the limited performance of single image deblurring. So while single image deblurring has been extensively studied, it is still a very challenging problem, and even recent state-of-the-art methods often fail to accurately remove blur. So because of the poor quality of deblurring results, this naive combination fails to reconstruct a sharp and clean radiance field, and as a result, novel view rendering also produces degraded images with the remaining blur as shown here. So to overcome these limitations of deep blur nerf and its variants, and also overcome the limitation of the naive combination of DNN-based deblurring and radiance field reconstruction, we recently developed a new approach called Deep Deblur RF, which we presented at CVPR this year. And our method is the first approach that adopts pre-trained DNNs for deblurring radiance fields, and thanks to that, it performs really quickly, and it is able to produce really high quality results, and it is also very robust to real world degradations. So the key idea of deep deblur RF is like this. So here we have a blurry input, and we can apply single image deblurring. And as I said, single image deblurring has limited performance. So so as a result, the deblurring result is not of really high quality. So as you can see here, this deblurred result looks sharper than this blurry image, but it still has some remaining blur here, and it has some it has some high frequency information that is lost. Okay, but fortunately we have multiple input images as we are constructing radiance fields, right? So we have multiple blurry images, so we have multiple deblurring results like this from multiple views, and then we reconstruct the radiance field, and this radiance field reconstruction basically aggregates complementary information from multiple views. So thanks to that, even if one deblurring result may have some degraded information, that degraded information may be restored by some complementary information from other views. Okay, so thanks to that, if we render new image for the same viewpoint of this blurry input, then this rendering result actually exhibit improved quality as shown here. So as you can see here, this rendering result has more high frequency details compared to this initial deblurring result. Okay, so based on this observation, our key idea is like this. We can use this rendering result as some kind of a guidance to remove blur, to more effectively remove blur from this blurry image. Okay, so this one provides us some hints about what the sharp image would look like. So we may use this image as a guidance. Okay, so we train image deblurring network to take these two images together, and to produce a deblurring result for this blurring input. So we call this step RF guided deblurring or radiance field guided deblurring. Okay, and then thanks to this guidance, we can more accurately restore high frequency details from this blurry input, as shown here. So as you can see here, this deblurring result has higher quality details compared to this rendering result. Okay, so we can actually repeat this process again and again, and we can progressively improve the deep learning quality. So based on this idea, we construct a pipeline like this as an alternating framework. So so this figure describes the overall pipeline of our method. So we have blurry training views, and to each of the blurry training views, we apply a single image deblurring. So which we call initial deblurring. So we after this step we have multiple deblurred results, and then we construct a radiance field using these deblurred results, and then we render guide images like this, and then for each blurry training view we concatenate that with each corresponding rendering result, and then we deblur the blurry training views again using this RF-guided deblurring network. And this one has higher quality information, and then we use these deblurred images again to reconstruct the radiance field, and we repeat this process a few times. So in our implementation, we repeat this process like 4 or 5 times, and then we found that 4 or 5 iteration is enough. And so also for this radiance field reconstruction step, we can actually adopt any representations. For example, we can use NURF or Prenoxel or 3D Gaussian splatting. Okay. So as the iteration goes, the quality of the novel synthesis improves like this. So this one is the result after the first iteration. So this one is the rendering result after the first iteration. So as you can see here, the high frequency detail is restored somewhat, and after the second iteration, we have higher quality details, and after the third iteration, we have even higher details like this, and after the fourth iteration, we have really high quality details like this. And as you can see here, the PSNR increases as well as the iteration goes. And in our framework, we actually have this RF-guided deep learning network. This is a neural network. So we have to train this neural network. So to train this neural network, we also proposed data set. So we proposed a synthetic data set, which is called Blur RF Synth data set. And we released this data set on our project webpage. And also we released a real data set, which is called Blur RF data set, a Blur RF real data set, and this data set is for evaluation. So, and we also released this data set on our project webpage. And this data set provides low light images with severe blur and severe noise and other outliers. And we are here. This slide shows the quantitative evaluation result. So the x-axis describes the training time, and this is a log scale. So, and this here this is faster and this is slower, and we have the y-axis describes the PSNR values or image quality of the novel synthesis, and these are all previous methods, and these methods are marked in star. These two methods correspond to our method, and Deep Deblur RFP is the Prenoxel version of our method, and Deep Deblur RFG is the Gaussian splitting version, 3D Gaussian splitting version of our method. So as you can see here, our method achieves highest quality results within really small training time compared to previous methods. And here we have some qualitative comparison. So on the left, we have a blurry input image. And as you can see here, we have severe blur and severe noise, and also saturated pixels here, which are actually outliers that cannot be modeled by traditional blur models. And on the right, we have deep blur RF. We have a result of the deep of our approach. So as you can see here, our approach can successfully restore high-frequency details. And we have another comparison, and on the left, we have a result of XBLURF, and this is another variant of D-blur RF, D-blur NERF. And as this XBLURF also relies on linear blur model, it cannot effectively handle severe noise. Okay, but so the rendering result has a lot of remaining noise and distortions like this. But unlike this result, deep blur RFP, which is our method, produces really clean, sharp results like this. And yeah, here we have another comparison, and on the right, this is a result of deep learning 3D-GS, which was presented at ECCV last year, and as the input image has a severe amount of noise, this one also fails to reconstruct a really sharp, high-quality radiance field. But in contrast, our method can reconstruct a high-quality, sharp radiance field while effectively suppressing noise. And even though I only described the motion blur caused by camera shake, we can actually apply our method for defocus blur too, because we can just simply train our networks for defocus blur. Okay. So this example describes that. So here, this image shows severe defocus blur on the background, and we can even with images with severe defocus blur, we can reconstruct a sharp radiance field while effectively removing defocus blur. So to summarize, in this work we presented the first RF deblurring approach that leverages DNN-based deblurring, and thanks to DNN-based approach, our method is can effectively handle real-world images, and it is also computationally efficient. And on the other hand, our method has a couple of limitations. Our method may fail when the input images have severe blur than those in the training data, and I guess I have limited time, so let me just skip this part. So let me conclude the talk. So in low light conditions, it is really important to effectively handle noise and blur to reconstruct a sharp, high-quality radiance fields. And several works have been proposed for handling noise and blur, but especially for blur. And most of them rely on multiple rate sampling for blur modeling, which is very similar to classical image deep learning approaches before deep learning. And because of that, they share similar limitations to traditional deep learning approaches. And to overcome these limitations, we developed the deep blur RF, which is based on DNN. And thanks to the effectiveness of DNN-based approach, our method can also produce high-quality radiance fields, even for images with severe blur and severe noise and severe outlier. Okay. Yeah, and that's it for my talk. And
thank you for the fantastic talk. Professor Xiang explored the challenges and innovations in applying neural radiance field and lighting limited conditions, such as the noise and blur images. This is a topic with great potential for both academic research and practical application in vision and graphics. Yeah, there is a question from the audience. To what extent do different blur colors affect the performance of the algorithm?
I'm sorry, can you repeat
Uh,
it again?
to what extent do different blur colors affect the performance of the deblur algorithms?
So the question is, yeah, to what extent our method can handle to what
Different blur colors.
yeah, so basically our method relies on deep learning based deep learning our method basically relies on deep learning based deep learning. So like the I'm not really sure about the size of the blur curves that the method can handle, but it usually like I don't know several like 30 pixels maybe, I guess. I'm not really sure, but yeah, to handle larger blur curves, we may just simply adopt more advanced, more sophisticated deep learning networks for these two steps. And we may also use some other deep learning-based deep learning approaches that use additional informations like gyrosensor information, or some other information. Then we may handle much larger blur than the current method. And definitely this one can handle larger blurs than the previous deep blur nerf and their each variant.
Yeah, I have a question. In low light environment, noise and blur can seriously affect image quality. When constructing high quality radiance fields, what are the other major challenges that need to be addressed except for the noise and blur? And
Yeah, so basically usually in single image deep learning blur can be caused by not only camera shakes but also object motions. Okay, so but we do not really assume dynamic target scenes here because we are aiming at radiance field reconstruction for the static scene. So for like for handling dynamic scenes that have object motion blur can be a interesting future direction, and some other factors. Mm, mm, yeah, usually noise and blur and some other outliers like saturated pixels are the most dominant factors that affect the quality. So and that affect the performance of the image deep learning. So those are the main factors. And besides that, where yeah um I'm not really sure for now.
yeah, okay, yeah. Yeah, yeah. There is another question from the audience. Which part of deep learning is the most time consuming? Which
Okay.
part is, yeah?
Yeah, so the most time consuming part is that so they basically so during the training, for the training of deep learner, they need to render blurred images like this. Okay, so to render a blurred image, they need to sample multiple ways, and so I come to so in conventional nerve process, we just sample single layer per pixel, right? But in the case of deep learner, we have to sample multiple ways. Like for example, we have to sample like a 5 or 10 rays. So it means that the training time may take like a 5 times or 10 times longer training time. So this kind of multiple ray sampling takes the most of the train is the most critical factor that slows down the overall training time.
Yeah. Okay. Yeah. Because of the time limit. Yeah. Let's thank Professor Shen Chu again.
Okay. Thank you.
Yeah. Yeah. Thank you. Thank you again. Okay. Now let's move to the lecture presentation. Yeah. The second talk is towards synergistic human AI content creation, given by Professor Zhe Wang. Professor Wang is an assistant professor in the Rust of Computational Media and Art and Artificial Intelligence at the Hong Kong University of Science and Technology, Guangzhou. He also holds joint and affiliate appointments in Division of Emerging Interdisciplinary Areas and the Department of Computer Science and Engineering at the Hong Kong University of Science and Technology. He leads the Creative Intelligence and Synergy Lab at HKUST. He received a PhD degree from the Department of Computer Science at Yale University and a bachelor degree from the Department of Machine Intelligence at PK University. He has published over 40 papers in top international journals and conferences. He serves on the committees of SIGGRAPH Asia, AsiaGraphics, etc. He also serves as a review for many journals. His research has been recognized by CCF, Tencent, Bird Fellowship, a Red Hat Bird Fellowship, an Adobe Research Fellowship, a Best Paper Award, and 3 Honorable Mention Awards. Now let's welcome Professor Yuan, please.
Okay. Thank you, Professor Wang, for your kind introduction. It is my great pleasure to be here tonight at the AsiaGraphics webinar. And today I'm going to give a talk on towards synergistic human AI content creation. So I'm going to start with traditional art forms and various creative tools that supported the creation of such art forms. So for example, in ancient Asia, we have the calligraphy, we have the brushes and mineral paints, and this has led to very famous traditional Chinese paintings like the one I show here on the left. And also, for example, for 3D content creation, traditionally we have the hammer and chisels, and those are commonly used for creating sculptures. As you can see on the right, that's a very famous sculpture by Michelangelo in the Renaissance. So moving on to the digital era, actually we have seen a great, such great development of digital technology that revolutionized content creation. So here on the left, we see Ivan Sutherland and his Sketchpad. That was back in 1963, almost 50 years ago. And back then, computers were huge, but they created this very innovative sketching-based interface that can render curves and triangles on the screen. And moving on to the late 90s, here in the middle, we have the very famous film called Toy Story, and this is actually the first fully computer-generated animation in computer graphics. And moving on, to most recently, we have a lot of new movies, films, games that highly relied on the development of computer graphics techniques and essentially content creation. So one thing that we may have noticed is that digital assets are typically unreasonably expensive. So here I show you an example of modeling an apartment building in Manhattan, New York. So here you can see that on the left, we first need to build the geometry shape, right? We need to build the mesh model for it. And then we need to do all the texturing, very highly detailed textures, and also UV mapping, things like that. Finally, we need to map the textures onto the geometry and also do the rendering, the lighting, all that kind of stuff. So here, as you can see, the first pass may take up to 22 hours to make it. And not to mention, you need to do that iteratively, right? You need to do a lot of revisions to make sure that your digital assets are desirable. Here's another example that I liked a lot. So this is a screenshot from a video game. And here you can see that every single digital asset, there is a label, right? There's a price label for it. And this is actually the cost to create for creating such digital asset. And one thing that essentially surprised me a lot is that you can see the pile of trash here on the ground, right? And that costs about 3,000 US dollars. So that you can see this is very expensive to make high quality digital assets for various digital content, including games and films and visual design. One of the reasons for that is that digital workflow can have a very steep learning curve. So here on the right, I have shown this is the interface of Autodesk Maya, and you can see there are a lot of buttons that you may not be very familiar with the function of those buttons. And if you want to create a 3D model of this architecture, this is the Ingolf drink on Yale campus. You can see there's a lot of interactions, a lot of operations that you need to do within this Maya interface. In contrast, if you look at the thing on the left, this is actually the original sketch drawn by the famous architect Eero Saarinen, who designed this architecture. And you can see here, he just used a few strokes, right? And also very few strokes, and for the this couple of sketches that can very intuitively convey the visual form of that architecture. So here, we can summarize that for sketching and interactions like that. It is very spontaneous and flexible. It can quickly convey the visual form, and it's very suitable for exploring ideas. In contrast, on the right, traditional graphics software, typically there are many buttons and windows, and 3D interactions can be unintuitive on a 2D interface. And this is also the reason why it is slow to iterate design ideas. So in this talk, I'm gonna talk about how the emergence of AI generated content or generative AI can help with this kind of creative process. And here I show some very, very early generative models back in 2022. And just after a few years, you can see there are all sorts of different generative models for images, videos, 3D models, and stuff like that. So a question I wanted to discuss with you today is how we can understand and enhance the creative process to build creativity support tools in the age of generative AI. So this is the center topic of our discussion today. So to explore how generative AI can help, we need to understand and create a more accessible and intuitive prototyping experience for content creation. And one of the key ideas is that digital tools should be able to understand and leverage users' creative process. So today I'm going to talk about a few projects that are actually at the intersection of computer graphics, human-computer interaction, and artificial intelligence. And there are all sorts of different medium like 2D, 3D, and even 4D. Okay, so today I'm going to cover four projects that centered at the idea of synergistic human AI content creation. So Magic Scroll is for scroll painting generation, And head evolver is for 3D head avatar generation. And NeuroCanvas is for more like scene generation, 3D scene generation with 3D sketches. And Anycraft is for animation prototyping in the MR space. Okay. So I'm gonna start with Magic Scroll. This is a project that we started a few years back, and this focused on enhancing immersive storytelling with controllable scroll image generation. And this work has been published at this year's VR conference earlier this year. So the background for this project is that visual storytelling typically uses non-typical aspect ratio images, right? So you can see there are various visual forms like comics and also scroll paintings. And you can see for storytelling, we need a lot of content. And also the aspect ratio may not be very regular, right? We may need a super long scroll painting to tell the story. There are three main different forms, like I mentioned comics, this poster, and also scroll painting. And if we look into that more at a more detailed level, you can see within this image we have different scenes, and in each scene we have different objects, right? So this is a concept we borrow from the Chinese literature theory, where we have the scenes and objects, and we use them together to create a coherent scroll image for visual storytelling. Okay, and also the motivation for that is, a few years back, it was very challenging to generate scroll paintings like those, because here you can see we tried some different models back then, and sometimes we don't have sufficient content, right? Some content are very repetitive, or we may have repetitive objects like what I show here. And also, there may be incoherent visuals, right? Because if you want to generate a very long painting, we have to make sure that the visuals are very coherent, across the scene. Or sometimes the style and layout are less controllable than we want it to be. Okay, so these were the research gap for this project. So in this work, we proposed a novel diffusion-based framework for generating scroll paintings, and also we can warp those images in different visual forms and display them and make users interact with them in VR. So here, I'm going to give you a brief overview of our framework. So again, our input is text, right? Just a piece of text that describes a story. And then our final output is a scroll image. So our pipeline is actually like this. The first is we have a GPT-based layout prediction, which is to predict a layout from input text using the power of GPT. And then we have a semantic-aware denoising, and this is actually divided into three different levels: foreground, middle ground, and background. And then we can also have optional control, like a reference image. And then finally, we can have something like this, right? So on the left, we have the input text descriptions, and on the right, we have the generated scroll paintings. So this is our framework. For a GPT-based layout prediction, I think one of the key takeaway is that GPT has the capability to predict reasonable layout from pure text input. So I think this has been used in other works as well, in other recent works. But here you can see that if we provide some instruction and some text, and then we can generate a layout for each object, we may have a bounding box, and GPT has the power to generate that purely based on text input. So I think this is really the first step towards controllable generation. And then for semantic-aware denoising, we actually have the standard diffusion process and also the multi-diffusion process, and then the latent blending, which is actually to blend the latent across three different levels, and finally doing the latent smoothing to ensure the final generation is coherent. Okay, so here I show you some examples of our effects of our design. So here, if we don't have latent smoothing, you can see we have some transition artifacts, which is not desirable. And if we don't have the object mask. So you can see sometimes they cannot generate the target very well, right? So supposedly there should be the sun here in the middle, but without the mask, it will not generate that well. And if you don't have the thin mask, sometimes it cannot be very well blended. So here you can see here the pagoda is like floating above the mountain, which is not what how we want it to be. Okay. So these are the three kind of ablation study results. Also, we provide color and layout control. So here, at the top is our full results. And if we don't have the text-based style control, you can see that for style-wise, it does not look like a traditional Chinese painting, right? Or if we don't have the image-based style control, right? So because we can provide a reference image to control its style. So without that, you can see the transition is not very coherent, and you can see the drastic change in color from left to right. So this is why we introduced text-based style control and also image-based style control. As an application, we can warp the scroll paintings in VR in different forms, different shapes. For example, we can make it like spiral or like a ring, or to make it like a deformed shape in VR, and this has enabled a wide range of applications in the VR space. Okay. We also have a data set we have collected a data set to actually train fine-tune our models. So they are divided into mainly 3 different categories. We have the traditional Chinese landscape paintings. We also have the comics. We also have the cinematic panoramas. So I'll put the link here at the end. So if you're interested in looking at the data set, I think you're more than welcome to do that. We do have some quantitative comparisons here. So you can see we have the different evaluations like the clip score or some other metrics. So you can see here ours is more coherent or more similar to ground truth, which is more desirable. And EA is for aesthetics. So in terms of aesthetics, we also have a higher score. And if you look at the chart at the bottom left, you can see that our results are very highly preferred by our users compared to other methods. Okay. So here it's aligned with human perception. We have improved visual coherence. And here you can see some quantitative comparisons. So here the last row is our results. So you can see here at the top right, we have some very repetitive objects, right? Very repetitive characters. Or here, right? Similar. But if you look at our result, you can see it's more coherent. And you can also see like the storytelling component, right? From left to right, it's like a cavalry are on expedition and then, cross through the mountains, and then finally they fight the dragon, right? So it's more like telling a story as opposed to other results that are more repetitive or less engaging for storytelling. Okay. So here we also have some more results. So in terms of Chinese painting generation, our style is also more coherent, and compared to others is also more aesthetically pleasing. And for comic strips, it's also interesting to see that ours can generate meaningful comics as opposed to others where they are not actually generating comics or some other content that are not coherent. Here is an example of the cinematic panorama where you can see our results are more storytelling oriented and high quality compared to others. Okay, so here are some other examples. One thing that's very nice about this work is that we can throw these scroll images into a video generation model, right? So you can see here, I'm showing some videos, and here you can see that it provides a very immersive tour into the picture kind of experience. So this is something that's enabled by our generated images together with video generation models, right? So here's another example. So you can see the waterfall, right, and the fountain. They are very consistent and provide a very immersive kind of experience. And all the input we need is a text description and a optional layout control. Okay. Here are some more examples. As you can see, we can also make them make them like a video, right? You can see the fly-through experience, and this has actually made this scroll painting generation much easier, as well as providing a very immersive experience. Okay, here is a drastic example. This is scroll painting generation with an aspect ratio of 40:1, right? 40:1, so it's very, very long.
In a serene garden, lakes and waterfalls flow gently as two girls, dressed in long skirts, run through it. The flowing water travels through dense forests, reaching vast meadows covered with green trees. Distant mountain peaks come into view, and amidst the ever-changing clouds, the mountains and waters harmonize. In this fantastical world, we gradually witness a series of towering castles standing in the distant lakeside, narrating an ancient story under the blue sky.
Right. So here you can see that, the kind of the generated results are very coherent and can be super long, although there may be some artifacts, but in general, it's very, very coherent and provide a very nice storytelling experience. Okay. So to sum up, we have our project page and code and data set here on this slide. In summary, we have proposed a novel diffusion-based framework for generating scroll images, and we have a various story-inspired visual forms and a VR system that shows the application of such methods. Okay, so for some future work, we can consider applying tokenizers and encoders that are better suited for ultra-long text. We may also introduce more conditional controls and enable more user interactions in this. Okay, so if you're interested in learning our work, feel free to go to this project page, and we have the code and data set over there. All right. So moving on to the second work, so this is more for the avatar generation, right? So we just talked about image generation, and then we move on to the 3D generation part. And this is something, the input is still the same, right? The input is still text, but we want to generate head avatars that are very expressive and also can be applicable to animation pipeline. And this work has been published as 3DV this year as an oral presentation. Okay. So as you can see, this is a demonstration of our work. So typically we need a text, right, like the Little Prince, and then we can generate a very high fidelity mesh model with the very high fidelity texture on it, right? And what's more interesting is that here at the bottom, we preserve all the animation parameters such as expression or pose, and also the character rig, the blend shapes, and also the UV mapping, the UV coordinates. So because our work is based on mesh deformation, all the attributes for animation can be preserved. And this is very, very useful as it can be compatible with the current graphics production pipeline. Okay. So there are some current challenges in text to avatar tags. So for example, some methods may not be able to generate very high quality meshes because it's concealed by texture. Or for implicit representations, they cannot preserve shape attributes, right? Because it's implicit, then all the blend shapes or all the shape parameters are lost. Or it may be over smoothing, right? So for example, if I want to generate a goblin, but some methods may not be able to generate the features in a very strong or very prominent style, right? Or the generation may be dependent on parametric models. So you have to have a parametric model like Flame or Simple in order for it to work, right? So if you don't have parametric models, then some methods may not work. So to tackle those challenges, we propose a deformation-based generation pipeline that takes a template mesh as input. Okay, so we do need a template mesh, and this template mesh can be anything. It can be a Flame model, or it can be any template mesh, as long as it has some good meshing, right? The quality should be good. The other input is text. So here we may input something like Terracotta Army, and then with the two input, we propose a deformation vector field, okay, to deform the template mesh, and then via a differentiable rendering pipeline, we can optimize the deformation field as well as the texture, the albedo map, right? And then finally, we can generate this very high fidelity Terracotta Army like what I show here in the middle. So so some of you may not be familiar with mesh deformation. So here I'm just gonna give a very brief introduction to it. So Neo-Jacobian field was proposed in each triangle on a mesh. And then via a Poisson solver, it can generate a mesh that's deformed right after deformation. So this is like how Jacobian field works. So you predict the Jacobian for each triangle, and then you use the Poisson solver to solve it so that you can generate an updated mesh or deformed mesh. So for our vector field, the key insight is that we use anisotropic scaling for the Jacobian field. The original Jacobian field, right, is isotropic. So in X, Y, Z direction, they all have to be the same. But here we use an anisotropic scaling, and the parameters can be learned via optimization. Okay. So to give you a more intuitive demonstration is, if you use the original Jacobian field, you can see that they're not very expressive, right? If you want to generate a goblin, but the years are not as prolonged as we want it to be. Okay, so this is a problem. So traditionally, if we have something like this, how are we going to tackle that, right? We just increase the learning rate, right? We make it, we make learning rate higher and wish for it to converge to a better result. But here, as you can see, if we just increase the learning rate, it may have the prolonged year, but the other parts actually are becoming worse, right? The other parts have worse quality and they're not stable. This is not what we wanted. So simply increasing the learning rate will not help. So this is why we introduce our vector field, right? Because this is anisotropic. So along X, Y, Z directions, they can all learn different weights or different Jacobian for that. So that you can see the years are prolonged and the overall quality are still good, and the optimization process is stable and converges faster. Okay, so this is the intuition behind it. All right, so as you can see here, this is the advantages of the vector field. You can see the terracotta army, the monkey, and the pig face. And the red parts are actually most deformed, right? So they have the strongest deformation. This is our visualization. And also with our vector fields, it converges much faster because it's a more expressive representation compared to the original Jacobian field. So here I show you some examples. So in the middle is our result, and we have some other baseline methods, and you can see we have much higher mesh quality compared to other methods. And here also we have some examples like the Superman and the Vincent van Gogh, and you can see if we zoom in, our mesh quality is still very good compared to other methods. And here is, after applying texture, they're very realistic. And it's also editable because it's mesh after all, right? We know how to edit a mesh. We know how to edit the texture map. So it's very good. And also it preserves all the animation parameters. So you can see if we make animation for one character and after deformation, the animation still preserves, right? We still have the same animation. We don't have to do that over again. So this is the advantage of our deformation-based generation method. Okay, you can do part-based editing. You can also add the texture based on text prompt. So we support various editing methods in our framework. We can also add some accessories, right? In Blender, we can add some hairs and to our model directly, and we can also support morphing between the two different models like this. All right, so this is these are the diverse results that our model can generate. Okay, can do texture editing, things like that. Okay. All right, so to sum up, we introduce a per triangle vector field to enhance the expressiveness of mesh deformation. And this can also preserve the 3D attributes. And our pipeline can be seamlessly used in graphics software, and it can be used as a plug and play solution for enhancing the deformation process. Okay, so this is our method. to generate the head avatar. And if you're interested in learning more details, feel free to scan the QR code. Our project page is over there to show you more details and results. Okay. All right. So given the time, I may go a little bit faster for the following two projects. We talk about image generation. We talk about mesh generation. Here, I also want to introduce to you our system for scene generation or scenic design prototyping by integrating 3D sketching and generative AI. And this work has been published at CAI last year. So scenic design refers to this kind of 3D modeling for stages, right? You may, if you go to a musical, if you go to Broadway, you may see some musicals like this, where at the background you have some stage set up. So traditionally, generating those are not easy. For example, we can do this sketching, but sketching is 2D, right? It's hard to convert to 3D. And we can also build like physical models, but it's very time consuming. So in our work, we wanted to understand how to create a system that can better facilitate scenic design prototyping. So here we have some 3 design considerations. So the system should support efficient creation of appearance. So appearance is very important. And also intuitive externalization of spatial concepts, right? So we need to make our spatial concepts external by using our system. And it should also support rapid idea exploration and design iteration. So this is our design considerations. And we actually build a system like this. It's a lot of engineering effort. So I'll just show you how it looks like. Okay, so this is a web-based interface like this, and you can draw 3D drawings like that. And I'll show you how it works. All right, so you have a 3D sketching like this, and you can apply generative AI to texture it, right? To generate the texture for the 3D sketches, and you can, direct the camera to render different views and to create a 3D scene like this. Again, it's very immersive. It's generated using 3D sketching and a collection of generative AI tools. Okay. So we actually support various input to generative AI. We can feed in the current canvas to generative AI. We can also do the full screenshot and then ask generative AI to generate it based on the rendering of the 3D sketch. We can also give a current canvas and together with a background reference so that our generation can be more coherent. Okay. And for those of you who don't know what a 3D sketch is, it's actually very simple. It's just like we have multiple planar 2D canvases, and then you can project the strokes so that it's on 2 different canvases, and this is like a 3D sketch. So we added a series of image like AI functions like text to image, sketch to image, image imprinting, and also segmentation, things like that. And these AI functions are integrated into one platform. And this actually has made users very happy. They can use all the different AI tools together with their 3D sketch. Okay, so here you can see at the bottom right, these are the scenes that we generated. Okay. And we did a user study, but I'll show you some key results like this. So I think it's important that 3D sketching can offer a control over viewpoint for generative AI. So see, this is the same 3D sketch, but they are viewed from different camera positions, right? And then you can use that as a control to generate the images that you like the most, right? So the same 3D sketch, but you can view them differently. Another insight is that 3D sketching can improve the quality of input to generative AI. So here, after projection, we can revise the sketch to fix the perspective, right? To make the proportion more truthful. And then we can render that to, we can render the 3D sketch and feed it to the generative AI. Because generative AI is trained on proportionally correct images, so after this revising, our generative results will also be better. Okay, so this is a brief summary of this work. So basically, Neural Canvas is a web-based platform. It integrates 3D sketching and a collection of generative AI models so that they can facilitate scenic design prototyping. They can generate a 3D scene in 10 minutes or 20 minutes, as opposed to model everything from scratch, which may take hours or days. And I think an important takeaway is that 3D sketching could facilitate AI content creation. All right. So finally, I think I may not have a lot of time to discuss the details, but I'd like to introduce to you one of our recent work called AsiaGraphics. This is for character animation prototyping, okay? And this has been published at WIST last year. So animation prototyping refers to something like this, or like animation pre-visualization, right? So on the right is the final animation, but animators would typically do something on the left first, right? To prototype or to pre-vis how the animations or how the characters would look like. But this is actually very exhausting, right? So if you ever did animation, it has a very steep learning curve, and you must go through a lot of time-consuming iterations. So we propose a mixed reality system, right? So this is in AR, and we used physical proxies to generate those animations, right? As you can see here. So we use a marker and this MR system, and then via spatial interactions, we can generate animation prototyping much more intuitively compared to a 2D software. Okay, so I'll just show you some examples. So here is how we generate the animation, right? So first, pick a character, and then we have this physical proxy that can be very easily made by hand. And this is like wire, right? And then we just position them in the physical space. And correspondingly, we have the virtual character that follow the same pose in AR, right? So this is how you generate this jump of the tiger, just in a minute, right? So this is how we do that. And we support various applications, like this is based on IK, inverse kinematics. We can also do the motion mode, right? You have the boxes where the chicken can follow the pace. We can also do this trajectory follow. Anyway, these are just different application scenarios, right? And I think through this way, we can see that it support applications like rapid previs or different characters and even environment proxy, right? So here you can use our physical proxy or the box as a virtual camera, right? So you can pan the virtual camera in the physical space so that you can get your ideal shot. Or you can leverage the physical attributes. So these are the magnets, and the magnets actually attach to each other, and then you can see that this represents how the eagle catches the cat, right? So it actually uses the physics of the magnets. And finally, we can use environment proxy so that we can very easily visualize how our virtual character can interact with our physical environment. All right. Okay, so just a few quick takeaways. So our AnyCraft framework can prioritize intuitive studio interaction for novice-friendly animation prototyping, and it supports multiple levels of detail, and it actually focuses on the impact from materials, right? So we want to make the 3D animation in a 3D interface, right? So we don't want to rely on a 2D interface on a 2D screen, but rather a spatial interface where users can interact with physical proxies to make this animation prototyping experience much more intuitive and convenient. Okay. All right. So to sum up, I think we wanted to cover a vision, which is synergistic creative intelligence. I have shown you how different AI models can help, like the image generation, 3D generation, right? But also, I think it's very important to understand the users, right? So how users would interact with these AI models in the creative process. So this is what I call synergistic creative intelligence. And actually, there are still a lot of challenges remain, right? So I think computing or AI should support creativity by inferring creative intention, right? So understand how users work during their creative process, and can also reduce tedious repetition. I think AI is getting better and better at this, and also explore broader design spaces. Okay, so I think in the era where the digital assets are ubiquitous and increasingly important, the digital tools for creating them, I think, are the new coal and electricity in this current AI revolution, right? So I think it's very important to pursue the goal of creativity for all. And I think to pursue that, we have to pursue interdisciplinary research where we need to do graphics and also HCI and also AI together to better understand this and to create a bright future for creativity for all. All right. So a final note that is our group is still looking for PhD students. So if you're interested in the audience, if you're interested in our topics like sketching, AR, VR, and AIGC, feel free to check out our website. There are a lot of many recent works, including SIGGRAPH this year. Feel free to check them out and reach out to me if you're interested. And these are some of our photos of previous events and our lab space. So if you're interested, do not hesitate to reach out to me. With that, I'd like to thank you all for coming. And these are my contact. And if you use WeChat, we have a QR code for that. Thank you very much for coming here. And I'm looking forward to taking any questions. Thank you.
Thank you. Thank you for the fantastic talk. Professor Wang shared with us four outstanding recent works, exploring how AI and human creativity can be meaningfully integrated to shape the future of digital content generation. I have questions. In your 3D head avatar generation, mesh deformation techniques are applied. Can you guarantee that the deformed mesh is free of self-intersection?
Yeah, thank you for bringing up that question. It's very important. So because Neuro-Jacobian field, they work on manifold meshes. So the template mesh, we make it a manifold, and after deformation, it is still a manifold mesh. So as you can see, this is one of the reasons why our deformed avatar has very high quality. But in terms of self-interaction, I don't think we guarantee there is no self-interaction. There may still be some, but I think we did a metric, and actually I think this self-interaction or the artifacts are minimal compared to other methods because our deformation is based on the template, which has very good quality. So this is how this basically works.
Yeah, you mentioned your method can generate high quality mesh. So how do you evaluate the quality of the mesh?
Yeah, that's a very good question. So let me show you some of our evaluation. This is mainly to as you can see here, right? So we are mainly comparing our method with other text to avatar generation methods. And as you can see, some methods are based on implicits, right? So based on nerves and stuff like that. And then if you convert a nerve to mesh, then of course it's going to be very noisy, as you can see here in the middle. So our mesh is based on deformation from the template mesh. So visually we do have more higher quality. And we also did evaluation with the users and see how they what they prefer. And I think this is also part of the evidence that our deformation based method is more has more high quality compared to others.
Okay. There is a question from the audience. When generating motions in MR, do you encounter situations where some actions cannot be detected?
Yes. So let's see. I think this question refers to the final work on this. So again, because of time, I may not have explained this in much detail, but it works like this. So first, we create a physical proxy. As you can see here, it can be some metal wire. It can be some paper folding, right? Some origami. It can also be like any physical, like everyday objects. And how this works is that we attach some markers to it. And these markers are typically used in mixed reality. And then here we have the 4 cameras pointing at a workspace, like I show here. So ideally, we want those markers to be seen by the cameras so that we can triangulate its 3D position. So this is very important. But most of the times they can do very well. But if you have, for example, if the marker is out of view, then it can be very challenging for it to estimate the 3D position. And as you can see, currently the marker are a planar piece of paper. So this is also one of our limitations because the marker may be seen by one camera, but not the other because it's very thin piece of paper. But in the future, we can explore more like hardware opportunities, right? Maybe you can use other signals so that we can track the physical proxy much better for creating those animations.
Okay. I ask a follow question. In your dual canvas system, 3D sketches are used as an interactive media between human users and the AI model. However, common users often lack strong spatial and geometrical appearance, making it difficult for them to produce high-quality 3D sketches. In many cases, the input sketches may be quite rough or imprecise. How does your method handle this challenge? Or to what extent is the system robust to low quality and ambiguous sketches?
Yeah, this is a terrific question. So as I'm showing you here, this is an example of a 3D sketch. And you mentioned, sketching is not for everyone because, in our study, we invited professional designers and typically they are very good at sketching. But I think our system actually offers like what I show here. So if you input something that is rough, or maybe the proportion is wrong. So here, as you can see, after projection, the proportion is wrong here, right? So you can see that the windows should not be, like this. They should be the same size. So even if we, for example, even if I'm a novice user, after this projection, I can understand that I did something wrong. So I can revise that iteratively, right? So I can erase that and redraw that on this canvas from a different view. So this kind of interaction actually make sure that novices have the opportunity to revise them and to do that iteratively. So once they have this, so you can see this is like the revised 3D sketch. We can feed the 3D sketch to the generative AI, which can generate much better result. So this is kind of the interactive way to solve that problem.
Okay, we have another question from the audience. In complex actions, can the marker be occluded or blocked from recognition?
Right. So this is a very good question. This is also related to the previous one on the marker recognition, right? On the tracking. So here I show you how it works in practice, right? So this is how the user manipulates markers to generate those animations. So as you can see, most of the times it's okay because your hand, doesn't cover the marker all the time, right? This is something we don't want. So you can see typically we interact with markers like this. And in these cases, occlusions are not the biggest problem. But again, if you have more advanced, for example, infrared or other signals or IoT hardware, we can make this more robust because this is not only dependent on visual signal, but we can make it more generalized once we have more hardware, and so that the users can do the animation prototyping more intuitively using our system.
Okay, thank you, Professor Wang, again. And thank you, Professor Suyong Chu, and all audience. Let's see in the next session.
Thank you. Thank you for having us.
Thank you. If you are interested in today's talks, you can check the homepage of the AsiaGraphics. We have record the video. Thank you. Bye.
All right. Thank you. Bye-bye.
Bye-bye.
Thank you.
Thank you.